Good morning, everyone. Thank you for joining us for this webinar on structured text maths instructions in the Cscape IEC editor. The presentation is just under 19 minutes, so we'll jump straight into it. And if you have any questions, you can put them at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Today we're going to be looking at structured text math instructions in Cscape's IEC editor. Let's get started. Let's look at our agenda for today. We'll start by looking at a list of the mathematical operators and all the different IEC languages. We'll look at some of the more complex mathematical functions. We'll look at a data type conversion because when you're doing calculations in a PLC, you need to make sure that your data types all match so you can accomplish what you're looking to accomplish. We'll look at the order of precedence or mathematical hierarchy, not only among the operators and the functions for math, but also as they relate to other functions in the PLC. There'll be demonstrations throughout and we'll finish with a Q&A session. Now we'll look at the mathematical operators, starting with the essentials: add, subtract, multiply and divide. These are the fundamentals used in control language programming, and structured text allows you to craft concise, readable algorithms with them. Additionally, we have other operators to consider. Modulo, for example, is handy when you need to find the remainder after dividing one value by another. Absolute value, on the other hand, helps us to determine the magnitude of a result regardless of its sign. And don't forget about exponents and square roots, as they are readily available as our basic arithmetic operators. Now we'll explore structured text syntax through several examples on the screen. We're using standard arithmetic operations like addition and multiplication, as well as functions like modulo and absolute value. In every case, the result is stored in the variable on the left, which we've named result here for clarity. Remember to use the assignment operator to assign values. For instance, in the last example, we are raising the variable in to a power specified by the variable exponent. These examples offer a practical glimpse into structured text syntax. Now we'll look at some less commonly used but highly valuable trigonometric functions. These functions are deeply rooted in triangles, as the name suggests. Among them, sine, cosine and tangent are the most frequently used. You can see their definitions in relation to a triangle diagram on the screen. Later, we'll demonstrate how we can apply tangent to calculate essential data in a control application. While they might not be used as often, all these trigonometric functions find their place in industrial applications. Now we'll look at the units required for trigonometric calculations, which are radians. Whether you're working with structured text, ladder logic, or any other programming language, the OCS logic engine assumes you're using radians for trigonometric operations. If your application deals with degrees as inputs or outputs, don't worry. Conversion functions are available to seamlessly switch between degrees and radians. Now we'll look at logarithmic functions, especially base 10 logarithms. These are incredibly useful when you're dealing with data that spans a wide range of magnitudes. For example, if you're working with sensor data that ranges from a few units to tens of thousands, comparing them on a logarithmic scale can simplify analysis. So how does it work? A base 10 logarithm answers the question how many orders of magnitude is a value away from 1. Let's take an example. The base 10 log of 1000. It's asking how many 10x steps does it take to get from 1 to 1000. One step gets us from 1 to 10, the next from 10 to 100 as 10 is multiplied by 10, and the third from 100 to 1000 as again 100 is multiplied by 10. So the base 10 log of 1000 is 3. Using logarithmic scaling helps in comprehending and comparing large values with smaller ones, making it a valuable function to keep in mind. Natural logarithms are invaluable for analysing growth in various contexts, such as the growth of data in scientific applications. Unlike the widely known constant pi used in trigonometry and geometry, natural logarithms centre around another constant, e, which is an approximate value of 2.718. When we calculate e to the x, we're essentially finding the value that results from continuous growth starting at 1 and extending over x units of time. Conversely, if you know the final value achieved after starting at 1 and want to determine the time it took to reach that point, you can employ the natural logarithm calculation. These functions are accessible in structured text and other programming languages, making them versatile tools for growth analysis in systems like PLCs, including the Horner OCS. Now we'll look at some practical uses of mathematical operations that might be more apparent. We commonly employ addition, subtraction, multiplication, and division for tasks like linearization, especially in industrial settings where scaling of analog values is frequently required. You can implement linearization using straightforward equation y equals mx plus b, and we'll provide an example shortly. Additionally, there are specialized scaling functions available, including integer and real value scale functions, which we'll demonstrate later. Now we'll discuss data type conversion. Calculations often involve starting with an integer value and needing a result in floating point or vice versa. In structured text, we have a range of functions for efficient data type conversions. Now we'll briefly discuss the arithmetic hierarchy or order of precedence. The operators are listed in priority from top to bottom, with parentheses and absolute value at the top. We won't dwell on this chart, but you can review it at your own convenience. It's crucial to understand operator precedence to obtain the desired results in your application. We'll do a demonstration now showing you how to use structured text to linearize some analog values. We'll look at a few different approaches. So here we have Cscape, and our application here is written in structured text. One of the advantages of IEC is that you can mix and match multiple languages, but for this example here, we're strictly using structured text. So here we have this linearized routine, and for our first example, we'll use traditional multiplication, subtraction, and addition to linearize an analog value to an engineering unit. So here we have a sensor, which is a 4 to 20 milliamp pressure sensor. So its range is 4 to 20 milliamp for its output signal, and its range in engineering units is 10 to 100 pounds per square inch. Now when we digitize this 4 to 20 milliamp signal in the OCS analog input, we're going to be converting it to a decimal value between 0 and 32,000 counts. So what we're doing is converting between 0 and 32,000 to 100 psi in this example. We also have to keep in mind that the analog value coming in is an integer value, so we need to use one of those conversion functions. So we can take our analog input integer and convert that to a value or a variable that's in real format, because that's what we need to use for most of our calculation, if we want the result to be a floating point value. And then here is our calculation that we're making the old-fashioned way. So we're taking our raw analog value, which is going to be between 0 and 32,000 counts, and we're going to be dividing that by full scale. Full scale is 32,000 minus our minimum value, which is 0. And then we're going to multiply that by the full scale, or the slope of the pressure curve here, which is max minus min, or 100 minus 10, which is of course 90. And then we're going to add it to the minimum pressure value. So if we start out with a value of 0 here, we're going to end up with 10 as our result. If we go all the way to a full scale of 32,000, we're going to end up with 100 as a result, and that's what we want to happen. Now we'll see that on the bench. So you can see on the upper left we have our pressure sensor value, which is a value between 0 and 32,000, and directly below that is the converted pressure in PSI. So we can adjust the analog simulator here, as you can see the analog input going up and down, and you can see the result in engineering units going up and down as well. Now we'll go back to Cscape and we'll look at doing it a slightly different way. With this example, we want to make sure that you don't end up with under range values, because with some sensors you can get below 4 milliamps, and it could represent the fact that we have an invalid value coming in below 4 milliamps. In some cases, it's just slightly under range, and you may want to use it in the math calculation. In other cases, you want to make sure that you don't have that result. In this example, it's possible for the result to be effectively below 10. 10 is the minimum reading, based on if our value is below 4 milliamps, coming in just a little bit, we're going to dip below 10. So we've added some extra code here, a simple if-then statement that says if the result is less than 10 pounds per square inch, we're going to keep it at minimum there, just to indicate that we ended up at a value that is a minimum value. We don't want to go below that. So that was our first example. Now we'll look at our second example. For this one, we're going to use a function called scale real. This is a very useful function that's included in the math choices in structured text. And so what we're doing here is similar to before, but it's a little bit easier. So we're converting our analog input value to real. And then what we're doing with our scale real function is our input is our real value that's been converted from our analog input, and that's the first listing here. And then we have the minimum value coming in, which is 0, and the maximum value coming in, which is 32,000. We just made those constants, but they could also be variables. Minimum value going out is 0 and maximum value going out is 1. And we're using those because in this scenario we're converting from 4 to 20 milliamps to 0 to 1 meter. So this would be like a level sensor. And just like before, we've just got a simple if-then statement here at the bottom to filter out all the values below 0 meters because we don't want to have a negative distance there. Now we'll go back to the bench. So this time we can see there on the level sensor at the top right that our value is below 0. That's because we're feeding it from the simulator a value that's almost at 0 milliamps. So until we start raising the value up to the point where we get above 0, you're not going to see a result that is scaled because of that if-then statement we put in. But as the value increments, you can see the scaling is getting up towards 1 meter. So that's simple scaling, using the scale real function. Now we'll look at an example where you could use trigonometry for an actual application. So here our example is a water jet. So we're going to assume that this water jet has enough power and enough pressure to shoot water in a straight line. So we have a nozzle here that we can incline up from flat all the way up to 10% or so. And based on the incline angle, our water jet is going to shoot off a course at a different angle. Now the point at which that end of that water jet hits its target, that's what we don't know and what we want to calculate. It's our target height. The reason we can calculate this using trigonometry is because we're going to be measuring our inclined angle using an inclinometer. We're going to have a known measured distance between our water jet nozzle and our target, which we're going to say in this example is 20 meters. And because we know the angle and we know the distance to the target, we can use trigonometry to calculate the height at which the water jet is going to strike our target. So the way we're going to do that is using tangent. So the tangent of an angle is opposite over adjacent. So in the case of our example, our adjacent distance of the triangle is fixed at 20 meters, and our opposite side is the target height that we're trying to measure or trying to calculate. So if we solve for target height, we can see that we can just take the tangent of our incline angle that we're measuring, multiply by 20 meters, and the result is going to be the target height in meters. So that's what we're going to do in our second example for structured text. So we'll move down here to the trig routine that we have, which is really very simple. We do have the linearization code, very similar to what we did with our last linearization example. And then we're using the scale real function to take the inclinometer output, which is 0 to 5 volts. That is scaled between -10 and +10 degrees. So we're using the scale real function to accomplish that. Keep in mind, this is 0 to 5 volts, and our analog input in this case is 0 to 10 volts. So that's why you'll see these numbers as they are, because 10% of full scale is 10% of 3200. If you look at that count, it's going to represent 10% less than 16,000, which is midway through a 0 to 10 volt scale. And then -10 is the value at minimum output, and 10 is the value at maximum output. So we're using that scale real function to give us the result in degrees for the inclinometer. And then we have a few more of those if-then statements here to filter out values that are above 10 degrees and below 10 degrees, because those are the only valid numbers we should be getting from the inclinometer. So now that we have the degrees, we can use trigonometry to solve for the target height. And we have to convert first from degrees to radians because all trigonometric calculations are done in radians. So we're starting with our real value of our incline that we just linearized. The result is our incline in radians. And then we're doing our calculations. We just described the water jet height, or the target height, is going to be 20 meters, or 20 times the tangent of the angle. Now we'll look at the bench, and we'll move over to the next screen. We're incrementing the simulated value from the inclinometer, and as soon as the spray angle gets above 0, you can see the height of the water jet is incrementing up to maximum. So in this particular case, when we're 20 meters from target, the height of the water jet in this example application can range as low as 0, all the way up to what looks like 3.5 meters in this case. Now another thing we might want to do in this application, instead of solving for height, we might want to solve for angle, and so the inverse tangent calculations are available as well. So this is just an example of where you could use structured text to execute trigonometry in your application. Structured text, being similar to text-based computer languages, is widely used. It excels in handling loops, searches, and mathematical operations. Its capability for advanced math functions finds applications in various real-world scenarios. Moreover, basic math functions are indispensable across countless applications. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, I'm not currently seeing any questions in on that, so it's a nice and straightforward one. Next week, we do have a webinar on the overview of the enhanced IEC editor. So if you have an interest in that, the registration links are on the website as usual. So you can go and do those, and it'll be the same time again next week. Okay, I think that's everything covered today. Thank you for coming, and we hope to see you again next week. Have a good day.